Okay, so let's start this week's statistics seminar. Welcome, everybody. And today we have Dr. Giacomo Zanella from the Department of Decision Sciences at Bocconi University. His research lies at the intersection of statistics, applied probability, and machine learning, with a particular focus on Bayesian computation. And today he will tell us something about the scalable computation for Bayesian models. So let's welcome today's speaker. Please go ahead, Dr. Zanella.
Okay, thanks a lot. So first of all, thanks a lot for the invitation. It's really a great pleasure to be giving a seminar at your department. I mean, it's a bit obviously not as nice as being in person, so that's a pity, but on the other hand, it's nice that we can present things to each other on the other side of the ocean. So, so thanks again for inviting, and it's really my pleasure, genuinely. Okay, so today the title I give to this talk is Scalable Computation for Bayesian Hierarchical Model. It's a very broad title. I mean, it covers some work which I've been doing in the last 2-3 years, but actually then the presentation itself will be a bit more focused, obviously. And one thing before starting, so feel free to interrupt me at any time. I tend to go fast and to put too much material in the talk, so I'm very happy even if you stop me and I don't finish the presentation, then we can skip some parts. It's perfectly fine. So the context, it's the one of Bayesian hierarchical model in a very general sense. So as we are all familiar with, I guess, when you build a Bayesian model, you typically build it hierarchically or sequentially by a sequence of conditional simpler distributions. And then you put them all together and you get a joint model, which is potentially complex and describes your joint uncertainty on parameters and data. And this kind of a very general and successful paradigm because it allows you to basically specify structure inside the way you believe the data generating process was arising, and you specify it in such a way that then you can have interpretable inferences and you can perform probabilistic inferences on quantity that you care about. So there is a lot of work obviously in that direction, and this is a very general category that I'm discussing. Just to be concrete, one example, you can think, for example, at nested multi-level regression, where you have data, actually your parameters sitting on a tree. So you have a tree structure, maybe you have data that, for example, represent performances of students within a class, which then is nested within a school, which is nested within a district and so on. And so you have, at each edge of this tree, you perform, say, a regression. And then you have the likelihood, the data, which could be, again, linear regression or any generic likelihood. And what we care here, it's about performing Bayesian inference. So we want to approximate the joint posterior of beta and t in the notation here. Beta are the high-dimensional regression parameters, and t are the unknown hyperparameters, such as, for example, precision matrices. Most of what I'm going to discuss will focus around sampling methods. So we would like to sample from the posterior distribution here. And the main computational challenge will be given by the high dimensionality of the regression parameters. So that's just to set the context, to be a bit more specific, although still quite general about the kind of questions and research objectives that we're going to look at in this presentation. Broadly speaking, we're going to seek to perform computational inferences, Bayesian inference in a scalable way. So for example, we would like to have algorithms which scale to potentially large-scale hierarchical models. In the example of before, for example, you may have a large tree. And if you have a large tree, then you would have a large number both of data points n and parameters p. So we're going to look at asymptotic regimes where both the number of data points and parameter grow. The aim we're going to set for this talk will be to have a computational complexity which is at most linear in n and p. So we want the cost of an algorithm, for example, a sampling algorithm, to give us one sample from the target to be at most order maximum between n and p. In the models where I'm going to consider, actually n will typically be larger than p, so more or less you want linear cost in n. And for this talk, I will be calling this algorithm scalable. I think linear complexity for the kind of hierarchical model, random effect type models I'm going to consider, it's the right target to set because it's feasible, while going sublinearly without doing approximations, it's beyond the scope of current methodology, I would say. So linear complexity will be the target. Generally speaking, I will try to devise a theory and methodology which deals with the interaction between computational algorithms and statistical models. So I would like, for example, to understand how model structure affects the convergence rate of, for example, sampling algorithms. I think this is quite interesting, and in a sense, for example, in the MCMC theory, there is typically more work on generic and more abstract target distributions, such as, say, log concave, and rates of convergence there, while here I will be talking about structured data. And again, the sparse dependence and the graphical model will play a crucial role. So more specifically, most of this talk will be focused on cross-effect models. So this is, in a sense, obviously a subset of the aim I said before, but I think it's an interesting subset, and I will be talking a bit about that. So we're going to be looking at models where the dependent structure is not, for example, structured in a nested tree, but it has a crossed dependence. So for example, in the simplest version, you could think of data Yij, where I denotes the row in a matrix and J denotes column. And then you have each observation could lie anywhere inside this matrix, and you have a row effect and a column effect. For example, in the linear case, you would get Yij normal would mean mu plus AI plus Bj. And so here, for example, we will use a recommender system language where I denotes items and users, and we are interested in regimes where both capital I and capital J, so number of items and users, is large. So both the number of parameters and number of data point is growing. More generally, we will be dealing with cross-effect models of this form. You have a data point Yj for J going from 1 to n, and is capital N is the number of data points. The likelihood can be any generic likelihood, which depends on a linear predictor, where basically you have a regressor with some fixed effect A0 plus capital K categorical effects. And the focus will be on these categorical effects, because I will be assuming that the number of predictors in the fixed effects it's quite low or moderate, while the number of categories in the categorical factors can be very large. So IK, capital IK, can be potentially very large. Capital K will be small, so we have a few number of factors, but with potentially many categories. And this is kind of a common situation arising in categorical regression, multi-way ANOVA, and so on. It's just a generic, in a sense, dependent structure, which again is not nested but crossed. And here, P is basically given ignoring the fixed effects by I1 plus IK, and will be interesting in regimes where P goes to infinity. Often P goes to infinity sublinearly with N, but it could also be that it goes at the same rate as N. So these are the kind of regimes we're interested in. One motivating application, which we will discuss later, it's to model pre-electoral surveys in Spain. It's an application where my co-authors, Omiros and team, spend quite a bit of time on. And there, it's kind of a common structure in political science to use this kind of models. And there they have 7 factors, and the likelihood is a multinomial logistic one, for example, to model the probability of voting for a certain party. So, okay, the plan of the talk is I will discuss, as I already started, the overview of models, challenging objectives. I will discuss then the first more technical and specific part will be a complexity analysis for coordinate-wide schemes like Gibbs samplers, for example, on cross models. I will discuss how to recover scalability in the way I defined before, and an interesting connection to random walk on random graphs. I will then provide a generic methodology for the general class of cross models I discussed before, and then I will provide some theory for the what I call the full sampler, which considers both the high-dimensional regressors and the hyperparameters. Okay, so first of all, just a quick recap here. I will say things that probably are familiar to most people, but I want just to, for example, highlight a bit the difference between crossed and nested models, and why crossed models are interesting and computationally challenging. So in both cases, you have a high-dimensional set of regression coefficient and a low-dimensional set of hyperparameters, which here I denote as A and T. The algorithms I'm going to be talking about work by iteratively sampling from the high-dimensional regressions given the hyperparameters, and the hyperparameters given the high-dimensional regression. So that's a typical scenario. And the main computational challenge, the first one, it's actually sampling from the high-dimensional regression coefficient at order n cost, where n is the number of data points. So when you have a nested structure, this can help you a lot. There are various algorithms which are able to exploit the tree-like structure for computational purposes. We'll discuss a bit more later, while cross dependencies are computational harder for the presence of loops, for the fact that it's more difficult to partition data points, and so on. In the MCMC context also, more specifically, nested structures have been studied much more. For example, there is a lot of work on hierarchical centering and non-centering on the role of parameterization in hierarchical model, where hierarchical refers to nested multi-level models. While cross-effect models, up to a few years ago, they were not that much understood, I would say. So for simplicity, just to be more specific, think at Gaussian likelihoods. And in that case, what you have is the high-dimensional Gaussian, which is the conditional of A given T and Y, and we denote by Q the posterior precision. Even in the Gaussian case, doing computation for cross models can be challenging. And the reason is that you need to compute for example, you need to invert or factorize the matrix. So say that cost of sparse linear algebra, of SLA, it's defined by the number of flops that you need to compute the Cholesky of Q. Obviously, if Q was dense, as we all know, the cost would be cubic in the number of parameters, which is typically much larger than n. It may be maybe quadratic or cubic in n, depending on the sparsity level. While if Q is sparse, as again, we all know, there are a lot of algorithms which can exploit sparsity and reduce the cost of factorization to much less than order p cube, but how much less will depend on the sparsity structure. So on the specific, in some sense, design of the sparsity structure. For nested models, as I mentioned before, a tree-like structure of dependence. So the fact that your conditional independence graph of your parameters A given T and Y is a tree allows you to use algorithms such as, for example, belief propagation, which, if you're not familiar with that, is like an extension of Kalman filter to trees, which can perform computation at linear cost. And even if you use default sparse linear algebra packages, if you order the variables in the right way, you will get a linear cost in the Gaussian case. On the contrary, when you have cross model, you have a sparse Q matrix typically, meaning that for a lot of combination of factors, of categorical factors, you have no data. So basically you have a non-zero term in the Q matrix when you get a data point, because factors are a priori independent and the dependence comes from the likelihood. But this kind of sparsity structure, it's typically not, it's like unstructured in a sense that it looks a bit more like a random graph. So you don't have like a banded structure or a tree structure. Even if you permute your variables, it's hard to get to those kind of patterns which are like favorable to sparse linear algebra. And in fact, empirically, what you observe is that the cost of computing like the Cholesky, the cost of factorizing the precision matrix typically scales cubically with for cross random effect models, even if they're very sparse. So here I'm just putting some simulations. And here what you see, it's the three lines are the number of flops that are required by Cholesky factorizations which exploit sparsity to compute the Cholesky factor and how they grow with the number of data points. And you see that basically all of these here, the growth is cubic in n. And that's because we have a design where n is of the same order of p. Here it's quadratic in n, and that's because p is of the order 2 over p, it's of the order n to the 2 over 3, and so on. So in all these examples, regardless of the permutation that we use and on the specific sparse Cholesky factorization, we always get cubic complexity, which again, maybe for people which are familiar with these things is not so surprising. What the structure which you do have, however, it's, I will go back one slide, it's a k-parted structure. So what you do have is these big white blocks, meaning that each block of high dimensional levels of one factor, it's conditionally independent given the rest. So you can easily do block updates of one set of categorical regressors given the other. And so it's very easy to implement block coordinate updates algorithms such as Gibbs samplers, which are easy to implement and they cost order n. So here, what I'm plotting is the computational cost of Gibbs samplers, including also the number of iterations to reach epsilon distance from the target. So we'll tell later how I define that. So in a sense, this is simply to motivate, this graph is simply to motivate that even in the Gaussian case, coordinate-wise updates are appealing. And obviously what we're interested in is the general case, and there, this kind of discussion is still relevant because you could use Laplace approximations. But even there, even more block updates are appealing because you could do them without approximations. So this is to motivate why cross dependencies are computationally harder and why we are going to study coordinate-wise schemes. So in particular, we are going to study schemes which update one set of factors conditional in the others. As I said, we're going to mostly focus on sampling. So we're going to consider Gibbs samplers, which basically update one set of factors, AK, given the others. For K going from 0, which are the fixed effect, up to capital K, which are all the categorical random effects. But actually, everything which I discuss applies also to backfitting. So when you want to compute generalized square estimates, so you want basically to compute the map, if you think at it from a Bayesian point of view, and then what you do is coordinate-wise ascent. And basically these two, especially in the linear case, they have the same rate of convergence. So when we're going to do complexity analysis of rates of convergence in the linear case, everything we say for Gibbs samplers apply to also backfitting. And in fact, there is a kind of our line of research. There is a parallel line of research by the group of Art Owen at Stanford, where they use backfitting to develop scalable inference algorithms for, say, for example, generalized squares on cross-effect models, so for frequentist inference of cross-effect models. And finally, what we do is also what we discuss afterwards is also relevant to the convergence rate of coordinate-wise ascent variational inference methods. So again, I will be focusing on Gibbs sampling for simplicity, but you can think that what is really special, what is really important here is not the sampling part itself, but the block coordinates-wise update itself. Okay, so let's go on. So first of all, is there any question up to here? Okay, I will go on. So, we want to characterize the computational complexity of the schemes and see under which conditions we can, first of all, under which condition they achieve a linear complexity and when we can prove that, basically. So the complexity of these schemes, they are iterative schemes. So it's the complexity is given by the cost per iteration times the number of iterations that you need to get close to either the map or the target distribution. In the sampling context, the number of iterations depends on the mixing properties of the chain. And what we're going to study specifically, it's the so-called relaxation time, which is the inverse of the spectral gap. The way I like to think at it, it's that the relaxation times gives an upper bound to the number of iterations you need to perform to get one effective sample size in stationarity. So if your relaxation time is 10, it means that if in stationarity you run your MCMC for 100 iterations, you will get at least 10 effective samples. And that's what is written basically here with the ratio of asymptotic variances. So we are simply going to think of the relaxation time as the number of iterations. So we are simply going to define, the complexity as the cost per iteration times the relaxation time. In the context of Gibbs sampling, as we said, the cost per iteration is order n. And given that our aim is to have linear complexity in n, we need the relaxation time to be order 1 with as NMP goes to infinity. So we need samplers whose mixing time does not deteriorate, whose relaxation time does not increase with the size of data and parameters. In a sense, I would argue that it's more or less Gibbs type schemes are the only one which achieve this without approximation, so which are able to have order 1 mixing for higher dimensional distributions of increasing dimensionality. So we're going to do theory under sparsity and balancedness. So sparsity means that, as I said, we're going to assume that we don't observe a data point for each combination of categorical factors. So the matrix, or if you want the array of which contains all the possible levels of categorical factor is not full. So we observe a data point only for a small subset of those. Here I'm denoting by S the matrix in the 2-factor case, the matrix which incorporates, which describes for which combination of AI and BJ we do observe a factor. And typically in applications, these matrices can be very sparse. So we do want to have a theory which handles sparsity. On the other hand, one assumption that we make, which is in a sense not desirable, but is needed to get explicit, it helps us to get more explicit results, is the balancedness assumption. So we're going to assume that each row sum and column sum of this matrix is constant. So the row sum could be different from the column sum, but for each row, you have the same number of observations per row and same number of observations per column. So in the recommender system terminology, each user has rated the same number of movies. Each movie has been seen by the same number of users. We don't believe that these assumptions holds in realistic applications, but we use it to develop theory, and then actually a lot of the results we find, at least empirically, extrapolate beyond that assumption, and ongoing work is about relaxing that. So for Gaussian Gibbs samplers, we're going to focus, the first part of the theory will be for Gaussian likelihood. For Gaussian Gibbs samplers, you can characterize your rate of convergence in terms of the spectrum of a high dimensional matrix. So a lot of this work will be dealing with characterizing the spectrum of matrices related to the Gibbs type updates and understand how the spectrum behave in high dimensions, more or less. So the first result is that for Gibbs samplers, under the balancedness assumption of before, so incorporating sparsity, we are able to compute exactly the relaxation time of the sampler. So this again needs to characterize the spectrum of the matrix. The spectrum is not all explicit, so it's like intractable in some sense, but you are able to find the largest one. So you're able to bound all eigenvalues apart from one and find what is the largest one, despite not having access to the whole spectrum. So the result you get is that the relaxation time of Gibbs, it has this expression, which is basically order n maximum of n over I, n over j. So this is basically maximum number of observations per row and number of observations per column. This is not great news because in a lot of asymptotic regimes, the number of observations per row or column will grow. So unless for all categorical factors, the level grow linearly with the size of data, this relaxation time will grow. So the Gibbs sampler will mix slower and slower as you increase the dimensionality of the target. So for full designs, this is at least n to the half, and the overall complexity is at least n to the 3 over 2, which is not what we want. So the same result also for k factors. Here I don't give the details for simplicity, but it actually gets worse for k factors, and you can get up to quadratic complexity. So what is the intuition? If you're familiar with Gibbs samplers or coordinate-wise schemes, the typical slow mixing comes from correlation. And here we have a model where factors are a priori independent, and the correlation is given by the likelihood. So the prior is not, this is the opposite compared to nested. For example, in nested models, the correlation and dependent structure is given by the prior, while here it is given by the likelihood. And each observation imposes a linear constraint on the sum of our categorical factors. So if you put a constraint on a sum then of a priori independent random variables, the nice thing is that, well, the bad thing is that if you update one given the other, you will have a small conditional variance compared to the marginal variance, so you will mix slowly. But the nice thing is that it's enough to integrate one factor to go back to fast mixing. And again, here I'm putting some geometric intuition, which maybe is not obvious, but the point is that you have a codimension, you have a space of codimension 1. So if you look of two-dimensional marginals here, they are not singular. So you will get, so it's enough to integrate one factor basically to alleviate this constraint, because typically this constraint will be strong, since the likelihood will typically be stronger than the prior, but integrating one factor, it's enough to alleviate it. Was there any question? Okay. So what this leads to is what we call collapse Gibbs sampler, where the idea is that you want to integrate one set of factors. The way we do implement it for a variety of reasons is by doing block updates, which is equivalent. So you block update one factor with all the others every time you update the other factors. So we do joint updates. So here there is a typo. It should not be AK, it should be A0, AK. So we jointly update A0, AK from the joint distribution of A0, AK. And the crucial thing here is that we are blocking the fixed effects with each random effector, each categorical factor. And this, it's easy to do, at least in the Gaussian case, because basically A0 and AK taken by themselves, they have a nested structure. So you can use sparse linear algebra here and you get complexity, which is order n, and it's very easy to implement. When you have a non-Gaussian likelihood, it's still quite easy to implement because the only thing you need to find, it's a joint update of the, we use a metropolis testing update, which mimics the exact Gibbs update. And there is a lot of methodology to do that for two-level nested models. So we'll discuss it later, but in a sense, this can be done exactly at order n for Gaussian likelihood and can be approximately accurately at order n for non-Gaussian likelihoods. So, okay, so how does this Gibbs sampler mix? So we know that the intuition is that it will improve the rate of convergence. So what can we say about that? So here is one of the first key results. So if you kind of lost everything up to here, this is a good one to try to follow. So here, what we try to do is to characterize the relaxation time of the collapse sampler. So you can think of the collapse sampler as the good way of doing coordinate-wise updates, and we would like to show that it has good mixing properties. And what we can show is that the relaxation time of collapse Gibbs is of order minimum between N1 and 2 and this auxiliary relaxation time. So N1 again is number of observation per row and 2 observation per column. And T-aux is the relaxation time of a simple random walk on the conditional independence graph of the parameters. So basically on the bipartite graph between the I's and the BJ's. So you take the co-occurrence matrix S, which describes the pattern of observed data. This induces a bipartite graph between, say, item and users, and you look at how quickly the random walk mixes on this bipartite graph. So you take an item, you go to one of the users which rated the item. From the user, you go to one of the items which was rated, and so on. If this random walk mixes well, then the collapsed Gibbs sampler mixes well. So intuitively, we want this graph S to have a good connectivity. Okay. And this, I will not go into details, but the proof relies on the notion of multi-grid decomposition. So in a sense of decomposing the mixing of Gibbs samplers into kind of global parameters and residuals. And the residuals are really what converge according to this diffusion. So you have two kinds of convergences. The convergence of the global parameters, which is a geometric convergence with rate that leads to this N1 and 2, while the residuals converge according to a diffusion, which leads to these T-aux, just to try to give you very high-level intuition. So what is the implication of this result? Well, it's kind of a nice situation. Here we say a win-win situation, because the nice thing is that if you have a lot of observation per data point, then N1 and N2 grow, but actually this reduces T-aux. So the more observation, the higher the connectivity of the graph, and so the faster the mixing of the random walk. So in a sense, you have two things which are complementary, and the hope is that the minimum will be small, will remain small, because as one grows, the other decreases, and so on. So consider a few examples of graphs. Here, I'm making banded structure just for visual simplicity. So the one on the left, we have N1 and N2, which are small, because we have a few observations per row and a few observations per column. And the random walk mixes slowly, because the random walk, basically, you can think at it as a kind of Gibbs sampler on this discrete matrix. So you pick a row, you sample from the blacks, you pick the column, you sample from that. So this is strongly constrained, so it will mix slowly. But actually, N1 and N2 is small, so the minimum will be small. If you increase N1 and N2, you give a lot of room to the random walk, so the random walk will mix faster, and so T-aux will decrease. So this is the kind of complementarity I discussed before. But actually, another crucial point is that in practice, you don't get this kind of banded structures, as I said before, which is the reason why, for example, sparse linear algebra, the default version is not efficient. What you do get in applications is this kind of random patterns. And so the nice thing is that the connectivity of random patterns is very well understood. So here we can borrow from a lot of results from probability theory, which basically tells us that if you have a random graph, which is more or less unstructured, which is what you would get from, say, missing completed random observations, then this leads to a bipartite graph with a very good connectivity, actually with a near optimal connectivity. So random graphs are what are typically called expanders. So they have rate of convergence as small as it can be for the given sparsity level. In particular, there's a result, which is called Friedman's second eigenvalue theorem or Allen conjecture, which states that if you have a random walk on a uniform deregular random graph, which is similar but not equivalent to an Erdos-Shreni construction, and you have a very large number of nodes, then basically your spectral gap, remember that a large spectral gap means a fast mixing chain. Your spectral gap will be of order 1 minus 2 over square root of d, where d is the degree of the graph. So it's really remarkable that if you keep d fixed and send n to infinity, the gap doesn't go to 0. And actually, if you increase d, the gap goes to 1. So it means that if you increase d, if d grows with n, basically you will get more or less something which converges to IAD sampling. So you will get a faster and faster mixing random walk. So in particular, the relaxation time of this T-aux is of order 1 plus 2 over square root of d, more or less. So when you plug this together, you get that collapse Gibbs for missing at random balanced designs. It's of order minimum between n1 and 2 and plus over 1 over square root of n1 plus 1 over square root of n2. And this, it's uniformly bounded over all values of n1 and n2, and in particular, as n1 and 2 increase, it converges to 1. So we have what we call a blessing of dimensionality, which you also observe in applications, that when you have a very large cross-random effect model, actually collapse Gibbs type schemes converge typically in 1 or 2 iterations. So in a sense, you have this unusual situation that the higher dimensional the problem in this case, and in particular the higher the degree, the faster the mixing of the sampler. This holds for uniform, it's an average case result. So you could have, say, an adversarial design where things go bad. So it's not a worst case result, it's an average case result with respect to the design. So just to illustrate the simulation, here we set with simulation the theory. So we set k equal to 2 factors, number of rows and columns equal, and send them to infinity. And we observe each observation is present with probability 0, 1 and missing otherwise. This is not exactly balanced, so the theory doesn't apply, but you can pretend it was balanced and do a sense theoretical prediction. So what would be the value if the connection to the random walk was exact, and you get something which mimics very well the numerically computed value, which is not surprising because Erdős-Rényi graphs are very similar to balanced ones. And what you see is that the mixing time of Gibbs sampler increases with the size of data set. So the algorithm is not scalable, it's super linear, the cost. While the collapsed Gibbs sampler, you get this kind of blessing of dimensionality, where the first thing is that it's uniformly bounded, and even more, actually, it mixes increasingly fast in this case. And as I said, for example, there's a nice example in a paper by Ghosh et al., where they compute numerically for a pretty large e-commerce data set the relaxation time, and they found that is around 1.5, meaning that backfitting algorithms or collapsed Gibbs sampling algorithms will converge in 1.5 iterations. So in a sense, they're a very efficient and simple way of updating the high dimensional set of hyperparameters. So one extension, which, for example, maybe some of you have seen the first paper of this work, which was not present in the first paper, is a theory for general K, which is something that we're working at the moment. The theory I discussed before and the connection to random walks is specific to K equal to 2 factors. When you have more factors, it's more complex to analyze the spectrum of these high-dimensional matrices, but what we can show is the following bound. So consider now K factors, K categorical factors. You don't have only one random walk. So you have maybe item, user, and day, or sex, or other categorical factors. And then for each couple of categorical factors, you have a random walk between AL and AM. And the result basically says that if these random walks if all these random walks mix well, then the collapsed Gibbs sampler and similarly collapsed backfitting and so on will mix well. So in particular, we have a bound where we have a function of K, which is the number of factors, and this C of K can grow faster. Say like K square. So in general, it's tight and it's useful for moderate values of K, times the worst case auxiliary, the worst case basically relaxation time of the auxiliary random walk. So you still get this connection. Before there was more or less an equal there. Now you have a bound. But what it implies is that if you have, again, random designs with a general number of factors, you still get the blessing of dimensionality, which is, again, something that we observe in practice. So if you get a corollary, a case where you have the number of factors being either fixed or growing sublinearly with n, then what you can show combining this result with Allen conjecture type results is that the relaxation time of collapsed Gibbs is upper bounded and will converge to 1 as you increase the size of this k-dimensional tensor. So this is something that we're working on at the moment. And finally, just to reconnect to sparse linear algebra, you can actually do a bit of theory in this case, meaning that you can prove a lower bound, which is quite easy to prove, for sparse linear algebra, for exact sparse linear algebra methods, which compute the Cholesky factor of Q. And this is of order k cubed. Which apart from the k cubed, what matters is it's about the capital N times m bar, where m bar is the average number of data points per parameter. And this lower bound matches the upper bound that we have for collapsed Gibbs, at least for k equal 2. So if you ignore T aux in the maximum for the upper bound of collapsed Gibbs, you get exactly order n capital N times m bar. So this bound in the middle, it's not tight. Typically collapsed Gibbs is much faster than this, and SLA it's much larger than this, at least for random designs, but it's enough to kind of differentiate the two. So you could do, there is a bit of theoretical arguments here to compare the two. So to recap on this part, empirically we observe that doing exact direct methods which require inverting or factorizing the matrices for cross-random designs have a cost of order p cubed. This is very different from tree-like structures. And what I think it's interesting is that direct methods here perform well on structured designs, such as trees, banded grids, and so on. On the contrary, coordinate-wise updates, such as collapsed Gibbs, perform well on unstructured designs, such as random graphs, while they can perform very badly, say, on banded designs. So in that sense, there is a complementarity between the two, and we argue that for typical cross-random effects, coordinate-wise updates are very effective and simple to implement method which can scale to large scale number of levels. As I said, this theory, it's for Gaussian likelihood, which in itself is already a practically relevant and interesting case, but we're also obviously interested to the generic case where you could have generalized linear regression or any type of likelihood. And what we said here is that we're going to approximate the collapse Gibbs sampler, the exact collapse Gibbs sampler. Here, the idea is that you just need to do a joint update, an efficient joint update of the fixed effects with one categorical factor. And that's much easier. So you could use many kind of tools from the MCMC literature. The one we use here is hierarchical centering. So we center one factor, and then we use the fact that A0, given the centered factor Xi, it's conditionally Gaussian, so that's easy to update. And then the Xi ik of k, which are the centered effects of level ik of factor k, are conditionally independent. So you never need to do a joint high dimensional update. You have to do a collection of ik low dimensional updates, which you could do, for example, using gradient-based samplers. And typically the dimensionality of these parameters is over the 1, 2, 5, or this kind of, say, below 10. So this is easy to implement. And in some cases, you can show that it matches closely the exact Gibbs sampler. But in general, we check it empirically. There are good theoretical reasons why you expect to do so. And in particular, what we observe in practice is that when you replace exact Gibbs with metropolis within Gibbs, for example, here I'm illustrating linear model versus logistic model, you do get a similar trend. You get, as you would expect, a bit of slowdown in the convergence, but that's a constant factor which does not depend on the dimensionality. And you again observe this kind of blessing of dimensionality. So in this graph, what I'm showing is the first line, it's the linear case, where we do exact collapse Gibbs. The second line is a binary observations case, where we do metropolis within Gibbs with the default gradient-based samplers. And what you observe, it's in yellow, the empirical, say, relaxation time, which in a sense the estimated integrated autocorrelation time, which you can think at as an empirical estimate of the relaxation time for some parameters. For orange is the one for Gibbs without collapsing, and you see that it mixes lower and lower as you increase the number of observations and parameters, while in blue is for the scheme with collapsing. And in black is for the regressors, in dashed, sorry, the solid line is for regressor, the dashed line it's for precisions. So the key point is simply that the pattern in the first row and in the second row is similar. So you get, at least empirically, metropolis within Gibbs, which approximate well the exact Gibbs sampler has similar performances. Here, just a couple of illustrations. Both are actually moderate scale, but just you could easily scale it to larger cases. Here, first we show we consider an ATH structure evaluator data set. Here you have k factors. We fit the model with the Gaussian likelihood, so this is a linear case, and we compare the performances to HMC. So in this case, I simply want to mention quickly that you get a significant improvement. It's around 1 to orders of magnitude improvement. And again, this makes the point that for structured models with, say, random effective models with sparse dependence, if you do coordinate-wise updates in an appropriate way, you typically get more scalability than if you apply black box gradient-based methods, which you would expect because in a sense you are exploiting more of the structure of the model. And here the idea is that vanilla Gibbs has a low cost per iteration, but mixes slowly, so requires many iterations to converge. HMC converges fast, but has a very high cost per iteration because it does a long integration time, many leapfrog iteration step, while collapse Gibbs has both, it's both computationally cheap and converges fast. And this kind of, again, this model is not huge, but again, something like LME4 package would take 40 seconds to fit this model, which is comparable with what MCMC takes here. So just to say that even frequentist inference here, it's not straightforward. A second illustration, it's the Spain selection data. Again, here we have just a multinomial logistic likelihood. You have around 200 parameters, which is not that much, but still is high dimensional enough to be challenging for default schemes. And we compare again collapse Gibbs with Hamilton and Monte Carlo. And we, again, you see that here, this plot, it's autocorrelation function as a function of wall time. And again, Hamilton Monte Carlo mixes well, but needs to do a very large number of leapfrog step per iteration, and so you get in the end the large time per iteration. So this is again to challenge the fact that Gibbs type schemes are in a sense inefficient compared to gradient-based ones. Finally, to conclude, I still have time. We want to spend 5 minutes on some ongoing work on the scalability of the so-called of what I refer as full sampler. And what I mean is that up to now we have done theory, which is focused on the conditional update of A, so of the high dimensional regression parameters given Y and T. And both, and here what you observe empirically is that when you are able to do that efficiently, typically the whole sampler, which alternates the update of regression and hyperparameters, so regression parameters and precision hyperparameters mixes well. But this obviously is not guaranteed in general. And so we would like to do theory which guarantees, which bounds the, which proves the scalability of the whole algorithm, the actual one you implement, with both hyperparameters and parameters unknown. Here, I'm plotting some numerical bounds for the epsilon mixing times. So these are a bit more still numerical, but more principled and refined than just looking at ACFs, our correlation functions. And what they show, these kind of violin plots are basically bounds. The expectation of this violin plot will give you a bound to the epsilon mixing time. I think here epsilon is 0.01. So this is the number of iterations you need to get to 0.01 distance in total variation for the whole high dimensional joint distribution of A and T. It's quite impressive that after, say, between 5 and 10 iterations, the sampler manages to converge, and this seems to be stable with respect to dimensionality. So this is also quite nice for people that are familiar with this coupling MCMC methodology, because this allows you to do, say, early stopping for MCMC in a sense that you could run the Gibbs sampler for around 5 iterations until they coalesce using this kind of coupling methodology, and this will give you an unbiased estimate. So it's also very practical to run only a few iterations of this sampler for large-scale models. So we want to prove basically that this is true, in a sense, what empirically it's suggested. So we want to seek order 1 convergence results for the mixing time of the joint sampler. So let's define exactly which mixing time we're going to use. So given a pi invariant Markov transition kernel P, we define the associated standard mixing time as the total variation mixing time with starting distribution mu. So this is the first time where the distribution of the chain starting from a distribution mu, which could either be a Dirac delta at a point or a diffuse start. After T iteration, the first time that its distribution is close to pi in total variation distance than epsilon. So this depends on the starting configuration, and then we consider a worst case mixing time from M warm starts. So M warm means that we assume that the starting configuration it's absolutely continuous with respect to the target, which means in practice that you need to take a diffuse start configuration. And we assume that the random nicotine derivative is upper bounded by M, where M is a fixed constant. And I will come back to how realistic is this assumption later. So we're going to define T mix epsilon as the worst case mixing time from M warm starts. And we want to study how this behave for collapse Gibbs as n goes to infinity. So in particular, as I said, we're going to study the behavior of T mix epsilon as both n and p go to infinity, and we're going to take a random design, a random data assumption. So it will be an average case analysis. And to do that, we define a sequence of target distributions, which we denote as pi n, which are the posterior distribution for when observing n data points, and we will have both n and p. So p will be a function of n, and it will grow with n. And this posterior distribution will be a function of the data, which are in this context a random variable. So we assume that the model is well specified, so that the data are generated from the true model with some fixed parameters, fixed hyperparameters. And we denote Pn to be the associated operator of the 2-block sampler. So just a sampler which alternates regression and regression coefficients and hyperparameters. So we get a sequence of mixing times, T mix n of epsilon. And what we show basically is that the lim sup of these mixing times for fixed epsilon, as n goes to infinity, it's finite. So this basically means, and this happens almost surely, where almost surely is with respect to the randomness of the data. So basically, this is the result we want, because it tells that the mixing time of the joint sampler, it's order 1 with respect to n and p. At the moment, we have proved the result for both nested and cross model with Gaussian likelihood. This is very much ongoing work, and in a sense, the proof strategies I will now briefly discuss is not very much related to Gaussian likelihood. So we are hopeful to extend that beyond.
Dr. Zanella, you have roughly about 5 minutes.
Okay, thanks a lot, great. So just to recall here, this is a mixing time for the joint distribution of precision and high dimensional Gaussians, which is intractable even in that case. So it's not jointly amenable to, say, direct methods such as sparse linear algebra. So just very high level proof strategy, I think that's quite interesting and promising in the sense that what we do, it's relatively simple. And that's why I believe it's interesting in the sense that we don't prove a bound. What we do is we don't prove a bound to Tn mix for fixed n and then see how it scales as n goes to infinity, because that would be very hard. There is a lot of work in probability theory on that. Proving tight bounds for this mixing time is very hard. What we do in this case, we actually analyze the limiting chain. So we first take the limit n to infinity, roughly speaking, and we see what are the limiting properties of the posterior and of the Gibbs sampler operator. To do that, we use posterior asymptotics. And obviously that's a bit tricky because you have a high dimensional regime where the dimensionality of the posterior grows, but the Gibbs sampler lends quite naturally to kind of dimensionality reduction techniques. So we are able to do that. And if you explore the behavior of the limiting chain, in a sense, the limit of Pn, the chain in the limiting object, and this mixes with property order 1, then you can try to reverse engineer and use this property of the limiting object to prove properties of the sequence of mixing times, more or less. That's just to give you the very high level intuition. So one technical part is to show that the convergence of the operator is strong enough to preserve mixing times, for example. So one thing is that, so I presented the result with warm starts on the joint hyperparameter and regression parameter space. That would be quite unrealistic in practice, because if you have a parameter space of growing dimensionality, having a starting distribution whose random decoding derivative as a bounded ratio with respect to the target, it's impractical. So you would need basically to be able to sample from something close to the target as a starting configuration. But actually what we can do is we can relax the assumption and require a warm start only on the hyperparameters which have a fixed dimensionality. So this is very realistic and would be in practice satisfied by any kind of warm start, like sampling from a uniform region, for example. So that I would say is quite, we can make it realistic, the starting configuration. As I said, we expect the proof strategy to extend beyond Gaussian likelihoods. And this result directly applies to the case where you do a full block update, for example, in the nested case with belief propagation or sparse linear algebra of the high dimensional regressors. In the case where you have a like Gibbs within Gibbs or Metropolis within Gibbs scheme, actually you would need to glue this result together with the fact that doing Metropolis within Gibbs doesn't deteriorate the order 1 mixing. And we're working on that at the moment. So just to conclude, some contributions that we give in this line of research is to provide complexity statements and specify a methodology and set of algorithms to achieve order 1 inference for Bayesian inference on crossed and nested effect models. Especially the last part is relevant for nested. In doing so, we have a neat connection between MCMC behavior and the graphical structure of the model through the random walk. And we have early work on using Bayesian asymptotics to prove order 1 mixing results for complexity of MCMC, which I believe it's a strategy that could be applied much more generally. One thing which, for example, from practical point of view would be useful to do, also thinking at expertise in your department, it would be that here I compared Gibbs types updates with exact sparse linear algebra, so with exact factorization and simulation from high dimensional Gaussians. Obviously, you could go for approximate linear algebra tools, which are, for example, very common in, say, Gaussian process regression. In that case, we haven't explored that, and it's not clear exactly whether you could achieve order 1 linear complexity and order 1 accuracy. Obviously, Gibbs type updates here are more appealing because they are exact, so they preserve the correct stationary distribution, but obviously approximate SLA could be appealing also in terms of scalability. Take-home message here is that for large scale hierarchical model, it's possible to do Bayes linear complexity, and you need to do that, you need to exploit model structure. In that sense, the algorithms would be, there is more algorithmic design, is not fully black box, but I think that's needed to get, in a sense, genuine scalability. Here I put some main references. I'm citing the work we did. Obviously, there are a lot of other people that did relevant work on that. And the first paper, it's the analysis for the nested case. The second paper, it's the case where we discuss collapse Gibbs and crossed models for k equal 2. And this paper, it's more methodological, where we discuss methodology for non-Gaussian case. We compare to Sparsity linear algebra, and so it's more of a review paper and practically oriented paper if you want. And thanks a lot for listening. And I'm very happy to take questions or any comment or feedback.
Okay, thank you very much, Dr. Zanella, for a nice talk. And I guess we only have time for, say, one question. Anybody who wants to ask a question, please unmute yourself and go ahead.
Can I ask a question?
Cool, go ahead.
So thanks for the talk, Dr. Zanella. I have a question regarding the properties or interpretation of the relaxation time. So it measures how many iterations required to get one effective sample. However, regarding the epsilon mixing time that you introduced in the later talk, does it also give some properties or interpretation in terms of how many burn-ins required to reach the stationary distribution?
Yeah, thanks. That's a very good talk. It's a topic which is, in a sense, it's general. It's not specific to what we're doing and is well explored in the Markov chain literature. I would say yes, under, for example, warm start conditions. So you can use the relaxation time to bound the mixing time, provided, for example, you have some condition on the starting configuration, for example. So under the warm start condition, you can use the relaxation time to bound the mixing time. Generally, the mixing time is a bit larger than the relaxation time, but the mixing time refers basically to the spectral properties of the chain. So it tells you what is the spectral gap, and you can use spectral gaps to bound mixing times. And you would have, yeah, so I could send you references, but yes, there are bounds. The relaxation time also gives bounds to the mixing time, provided you have a warm start. I like to think more at relaxation time in this way because I think it's more natural, but you can also think at them as giving bounds to mixing times. I hope that helps.
So good relaxation time also naturally leads to the good epsilon mixing time. Is that
yes? So it's not through the mixing times. It's less or equal than the relaxation time by itself. You have a constant in front, which depends on basically the warm start condition in some sense. But you can have good bounds on mixing time starting from the relaxation time. Yeah, I could send you. I'm very happy to send you references more specific if you want.
Thank you.
Okay, I think that's pretty much it for today's seminar. And let's thank our speaker again for this very nice and clear talk. Thanks, Dr. Zanella. Bye.
Thank you.